Then we move to June Shintake. Do you think you can turn on your camera
Yes.
and perhaps you can share the screen?
Yes. Yeah. Just wait a moment, please.
Okay,
Right now I'm trying to share my screen. Okay.
excellent. Good to see you. And I think you are,
Oh, yes.
yeah, just go to the full screen and you're ready to go.
Do you see my screen right
Yes, you
now?
can see, but can you go full screen? Oh, we don't see the full
Oh,
screen yet.
oh, I see. Maybe there's something wrong with my connection to external monitor. Sorry for getting delayed. Now I'm trying to uh, stop and restart my sharing. Just wait a moment, please. All right. Now, I'm
Perfect.
hoping
Yeah,
that
yeah,
you
perfect.
guys
Please go
are
ahead.
watching full screen. Okay. Thank you very much for giving this opportunity me to share some of my work. So yes, so now, yes, in this talk, I'd like to introduce some of our developments on soft underwater robots. So uh, the reason behind making those soft underwater robots is that basically I like fish. So now I'm showing you a video that I got 10 years back in Okinawa Island. It's a smaller island in the south part of Japan. And as you can see in underwater, we can see so many different creatures and they have diverse morphologies and somehow they all adapting to uh, water environment, which is totally different from what we are being living now. This function having by fish fascinates me a lot. And then at some point, I yes decided to duplicate those real fish by a robotic approach to understand how they generate swimming behaviors. So good thing was that our background was on soft materials and devices. So now on the top of this slide, you can see devices that we developed recently. So I don't describe every device in detail, but we basically develop soft robotic device like soft pump, biodegradable actuators, sensors, and wearable devices. Based on the knowledge obtained by development of these devices, we decided to use soft electric actuator technology to realize underwater robot. So the technology is called specifically as direct reaction actuator. So you can see on the right side, it has kind of a membrane structure. And then on both sides, you have electrodes. Then when a voltage applied between the electrodes, basically they squeeze each other. And then the thickness is reduced. And eventually, the area is expand, as you can see on the right side. And we can exploit this electromechanical behavior as an actuation. So, and then on the left, this is an example of this type of actuator watching from the top. By applying voltage, you can see the movement of the electrode in black color. Okay, then we came up with an idea to adapt this actuator into a fish robot by having kind of layer structure as shown on the left side. So basically, we have a compliant body made of rubber, and on both sides, we have the soft actuator. And by actuating these two actuators one by one, basically we have a bending deformation of the body from which we expected to have fish-like undulated motion. This is what we got eventually. This is real time watching the top. And yeah, as we can see, by activating the two actuators one by one, eventually the robot showed like nice deformation, I mean fish-like deformation, and kind of efficient swimming movement, which is surprising because what we are applying is just on and off of the voltage, but somehow we are able to realize fish-like motion. Then, yes, at the time I got this result. Okay, so I thought that somehow a soft body can interact with external environments to, how can I say, to create kind of efficient deformation in water such that it can push itself forward. That's why we get this kind of nice behavior, swimming motion. Then this made me to develop underwater robot having kind of passive body. Then we went to making this kind of complicated fish-like robot. What we have is a structure mimicking bone and muscle of real fish. And then the fore part is moved by a submotor located here. All right. Okay. All right. And then this shows a test of the robot. This time, the body of the fish robot is completely passive, but as you can see, in the end, we get nice deformation, fish-like deformation. And then this robot swims pretty well somehow. For me, this is kind of intelligence already implemented in the body. And then after this study, we decided to extend this concept oscillating passive soft body by motor. So this is the what I got after. So now we have a flexible body connected to a brushless motor, which is quite powerful, moving the body like this. And then this motor is controlled by microcontrollers and receivers, so meaning that basically we can control this robot remotely. Then we made this architecture because at some point we realized that by using powerful motor, we could generate very agile robotic movement. Okay, so this is a video moving the body by a motor. So you can see that by oscillating the flexible body, which is actually a little bit rigid, it can bend like a fish body. And then, so now I'm playing the video on the right side showing turning of the robot. This is real time. So by having a body directly connected to a motor, it's possible to realize quite fast turning motion. So this is real time. It's because it's pretty fast. We cannot recognize the movement. So this is slow motion. And then you can see that the flexible body of the robot is functioning very well to balance the attitude of the robot. Okay, then after that, we went to swimming experiment in water pool. So now we are putting the robot in the pool like this, and then we start the motor. And we saw that the robot was able to swim very fast, like this. I think there's another scene watching outside. Okay, that's like this. For me, this is a good achievement. I mean, by combining rigid motor and a soft body, basically, it's possible to have agile soft under robots, which is comparable to real fish. So, yes, on the top side of this side, you can see the speed of the robot. So, which was more than 6 body lengths per second, which is comparable to real fish, as well as faster than most of robotic fish. Okay, all right, yes, and then finally, I'd like to share you some interesting robot. So this is to exploit interaction between liquid and liquid. So the idea is resulted from the fact that oil and water do not mix each other, meaning that there is an interface between two different liquids. And then by moving one of those liquids, basically we can make a reaction force to move a robot. Then we demonstrated this concept by using ferrofluid. So this is the movement of the ferrofluid in water. So the main component of ferrofluid is oil. That's why it can hold its shape. And then by having external electron magnets, we can deform the shape of the ferrofluid to make reaction force to surrounding environment, which is in this case water. And then now we are watching the robot, and as you can see, the robot can move forward. And also, we found that by changing the activation of this ferrofluid, it's possible to make rotation of the system. This happens by the interaction between liquid and liquid. This is a kind of a new concept of a soft robot. All right, let me summarize my talk. So, yes, so I want to say that basically soft under robots are very interesting platform to study embodied intelligence. And then this time, I'd like to have your opinion if those under robots could be useful for your study of embodied intelligence. Thank you very much.
Thank you very much, Jim. This was a fantastic presentation of how embodiment can be used in soft robots, and I think a very impressive achievement. Okay, I hope you can stay for a while, the discussion later. And then for now,